the previous lecture we were discussing this equation, which is the Cauchy or the Navier equation. The left hand side we discussed in both conservative and non-conservative form. While the left hand side is pretty clear what it intends to convey, we will now emphasize on the right hand side, and this emphasis is because of the following. What is our objective? Our objective is to solve for the velocity. In a fluid mechanics problem, this is a primary variable, velocity. So, let us make a tally of knowns and unknowns. So, what are the unknowns and how many independent equations are there? So, unknowns are rho may be an unknown, u1, u2, u3, and tau ij's, these are not known. So, 6 tau ij's, not 9 because 3 are dependent on each other. So, this is also called as momentum equation. In fluid mechanics, normally people do not call it linear momentum equation, because the fact that tau ij is equal to tau ji is embedded within this equation. So, angular momentum consideration is already embedded in this. So, what are the equations that we have? Equations means independent equation. We have continuity and 3 components of the momentum equation. So, we have total unknowns 1, 2, 3, 4 plus 6, 10, and number of equations only 4. So, these are not matching. So, we need to reduce the number of unknowns. One way of doing that is to express this in terms of the rates of deformation. For fluids, that is what you intuitively expect to do, because for solids the stress is related to the deformation. For fluids the stress will be related to the rate of deformation. However, when the fluid is at rest, there is no deformation. That is the definition of a fluid at rest or fluid static condition. Then still the fluid has some stress, and that stress is due to the pressure of the fluid. So, that is called as a hydrostatic state. That is a state where only the pressure distribution governs the state of stress on the fluid. When the fluid is under motion, it is the pressure plus an additional component which we call as deviatoric component. So, tau ij we can write tau ij hydrostatic okay. Now, tau ij deviatoric, it depends on what? So, if the fluid is under motion, its stress should depend on rate of deformation. So, the rate of deformation the general velocity gradient tensor we can write this is the general velocity gradient tensor, but this represents rotation and that should not give rise to any stress. So, the stress is primarily due to this one, which represents both angular strain as well as linear strain. When I equal to j, it represents the linear strain. When I is not equal to j, it represents the shear strain. Okay. So, the tau ij should be mappable to this one. Question is what kind of mapping? That is, tau ij is related to the rate of deformation tensor. Tau ij is a second order tensor, rate of deformation is also a second order tensor. So, we need to have a relationship between one second order tensor with another second order tensor. It could be linear or non-linear. If it is non-linear, it is called as a non-Newtonian fluid, where the stress and the rate of deformation, they are not linearly related. If the stress and rate of deformation are linearly related or linearly proportional, then this is called as a Newtonian fluid, because this is what is the Newton's law of viscosity. So, when we want to write tau ij, we should be able to write it as a linear mapping with E with some indices, because it is tau ij and the linear mapping will involve I and j as free indices. With E also we cannot write the same ij, because I and j are free. So, with E we can write instead of ij maybe kl. Okay. Now, more important thing is what transforms this second order tensor to another second order tensor EKL, that is a fourth order tensor. A fourth order tensor transforms a second order tensor to another second order tensor. So, this is for a linear stress strain rate fluid. There are some special types of fluids where the stress strain rate relationship is governed by this with some additional constant, but we are not bringing that special type of fluid into picture. So, if without that additional constant, if it is just linearly related, then this is called as a Newtonian fluid. Now, here comes the complication. So, this is what is there as a variable in the equation. This is what you have in terms of the velocities. So, these will not generate extra unknowns, but this will generate extra unknowns C, I, J, K, L, 4 indices. So, 3 into 3 into 3 into 3, total 81 unknown parameters it will introduce. So, that means to describe the property of a fluid, you would ideally require 81 constants. Normally that is never required. So, what it means is that definitely there must be a simplification to this for more realistic fluids, and we will consider such more realistic fluids now, which are homogeneous and isotropic fluids. So, first we consider isotropic fluid. Remember, this is tau ij deviatoric, this is not the total tau ij. Okay. Hydrostatic we will show separately how to write the hydrostatic stress. So, for isotropic fluid, you will have what is the property of isotropy? Say you have a coordinate system, coordinate axis like this. You measure properties with respect to this coordinate axis. Now, say you make an arbitrary rotation of this coordinate axis. So, by rotation what you are doing? You are essentially changing the direction. If along those directions also you see the same property, that means properties are direction independent, then that is called as isotropic. So, isotropic means direction independent. and when it is isotropic, we will try to form an isotropic scalar starting withCijkl. So, we want to convert thisCijkl, a fourth order tensor, to a scalar, then we will consider isotropic scalar. So, it is our task is cut out, we have a fourth order tensor, we want to convert it into a scalar. What is given to us is some set of vectors. Why we are dealing with vectors? Because isotropy will essentially be dictated by how the vectors are oriented. So, how many vectors will be required to make this scalar? See, when you multiply it with something with the same index, then that index is gone because there is a summation over that index. So, if you have something with I, then that summation will take I off. Similarly, another with j, another with k, another with l. If you do that and multiply that entire thing together, then I, j, k, l, all those indices with the summation will be gone and then it will be converted into a scalar. So, you require 4 vectors. One vector will donate the index I, another vector will donate the index j, another vector will donate the index k, and another vector will donate the index l. So, let us try to form a scalar. Four vectors a, b, c, d each has donated one index. Now, this scalar could be isotropic, anisotropic, whatever. If it is isotropic, then so let us draw these vectors. Say this is vector a, this is vector b, this is vector c, this is vector d. So, if the propertyCijkl, the properties originated fromCijkl are isotropic, then S is isotropic. That means the orientations of the axis A, B, C, D are not that important. What will remain important? The angle between them will remain important, because that is what is preserved even after rotation. After rotation, the absolute orientation changes, but the relative orientation, that is the angle between two vectors, remains conserved. So, we can write this if it is isotropic, let me write it and then I will explain what I intend to mean, it will be clear to you. So, how many combinations are there? Taken 2 at a time. A can come with B and then C will come with D. A can come with C and then obviously B will come with D, and A can come with D, then B will come with C. So, 3 combinations are possible, right. So, the 3 combinations, and this is essentially what? This is the dot product of the 2 vectors A and B. AI BI is essentially A dot B. A dot B will automatically give the cosine of the angle between the 2 vectors. Okay. So, the angles between the vectors that is given importance, but not their absolute orientation, and then these constants alpha, beta, gamma are arbitrary mathematical constants. So, we are able to write thisCijkl story with 81 indices in terms of the 3 indices, but these themselves could be variables, these may not be very constant indices, but if it is a homogeneous fluid, then this will not vary with position. Homogeneous means varying with position, not varying with position. Isotropic means not varying with change in direction. So, if it is a homogeneous fluid, then alpha, beta, gamma are not position independent. Not position dependent rather for homogeneous fluids. So, then we will do a little bit of manipulation. See, we want to write this like AI, BJ, CK, DL. So, we want to switch indices, and there is a very well known friend which helps us to switch indices, and that in Cartesian index notation is known as Kronecker delta. So, Kronecker delta, what it does is something like this. It is defined like this, it is also a second order tensor. This is defined as 1 if j is equal to I is equal to 0 otherwise. So, you can write for example Aj or Ai rather is equal to Aj into delta Ij, right, because delta Ij is 1 only when j is equal to I. So, when j is equal to I, this j will become I, right. So, you can switch from I to j by multiplying with, or from j to I by multiplying with this. So, with this one you can write this as Ai. So, if you want to make it Bj, with what you will multiply? Right. Then Ck, then dl, right. It does not matter because delta Ij is symmetric, you could write delta Ij or delta Ji, this you could write delta Lk, delta Ki, all these, that is the symmetry of tau Ij. So, sorry, let me just, so this is delta L, you want to, so you want to eventually have this as sorry dl, you want to have this as dk. So, if you write this as this, when L equal to k, this will become dk. So, that is what you want, it is the inverse of what we were writing. So, this you wanted to write Bi, not Bj. So, if you wanted to write Bi, when this j is switched to I, this will become Bi, right. So, this will be delta Ij, this will be delta Kl, okay. So, then plus beta ai bj is already there, ck c was earlier I, and right plus gamma ai bj ck delta jk, and then dl delta il. So,Cijkl ai bj ck dl will be equal to alpha delta ij delta kl plus beta delta ik delta jl plus gamma delta jk delta il, this into ai bj ck dl. That means by comparing these two you can writeCijkl okay. Now tau ij and tau ji, their deviatory components are the same. So, if that be the case, so tau ij deviatory I am writing in short d is equal to tau ji deviatory. That meansCijkl will be same as Cjikl, because tau ij deviatory isCijkl ekl. Tau ji deviatory could be Cjikl ekl. So,Cijkl must be equal to Cjikl. So, that means just you swap I and j here. So, alpha delta, so let us write thisCijkl I and j. So, delta ji delta kl plus beta delta jk delta il plus gamma delta ik delta jl, right. Now, these two get cancelled. So, from this equation you can clearly get that beta is equal to gamma. Okay. So, when you have beta equal to gamma, your number of equation, a number of unknowns comes down from 3 to 2. So, now you are able to write tau ij orCijkl first, right, alpha into delta ij into delta kl plus beta delta ik delta jl plus gamma gamma will be equal to beta delta jk delta IL. So,Cijkl into EKL, this is tau ij deviatoric. So, this is alpha delta ij delta kl plus beta delta ik delta jl plus beta delta jk delta IL into EKL. Okay. So, this will be alpha delta ij. What is free here? Free is I and j. These things you really cannot sum up. So, what summation will be on k and l? So, delta kl will be 1 when l equal to k, and then this will become ekk plus beta. Again delta ik will be equal to 1 when k equal to I, and delta jl will become 1 when l equal to j. So, this will become Eij plus delta jk will become 1 when k equal to j, and IL will become 1 when l equal to I. So, it will become Eji. So, this now what is EKK? So, let us write the expression for Eij here. So, Eij okay. So, EKK is E11 plus E22 plus E33, right. So, that is del U1 del x1 can you recognize what is this? This is the rate of volumetric strain, divergence of the velocity vector. So, this in short you can write del uk del xk. Plus beta. Eij is this one and Eji is the same thing. So, Eij plus Eji is simply this okay. So, this is tau ij deviatoric. So, physically this is what? This is related to volumetric strain, this is related to rate of deformation. I am not saying linear or angular, because when I is not equal to j then it is angular, but when I equal to j it is linear. So, it is better to say rate of deformation. So, you have tau ij deviatoric, one component related to the volumetric deformation, another component is related to the linear or angular deformation. So, this physically is nothing but the viscosity of the fluid, because the viscosity is that proportionality constant that relates the stress with the rate of deformation. That is the definition of viscosity through Newton's law of viscosity, and this we call another constant just to standardize it with the most of the textbook symbol. This is lambda or volumetric dilation coefficient, because this is related to volumetric change. Therefore, we can write the tau ij in this way. Now, tau ij hydrostatic, this is simple, but let us just complete it. Hydrostatic stress is only a normal stress, but it is acting radially inwards due to pressure. Pressure is always compressive in nature, pressure cannot be tensile in nature. To appreciate that, we write it as minus P delta ij. Why minus P delta ij? Minus P is pretty clear that positive tensile stress is plus, but pressure by definition is compressive. So, it should be negative normal stress. The other thing is that pressure is normal stress and not shear. So, pressure will be active only when J is equal to I, that is tau II, that is only normal, not shear. So, to sum it up, we can say that tau ij is equal to minus P delta ij plus lambda del u k del x k delta ij plus mu del u I del xj plus del uj del xi. What are the assumptions? Homogeneous and isotropic fluid, where these lambda and mu, these are constants, these are not functions of position. If these are functions of position, it will become inhomogeneous. It can still remain isotropic, but it will remain inhomogeneous. So, this is the formal way of writing the Newton's law of viscosity. As a teacher, this is a very important remark that I give you to all of you. When we introduce the Newton's law of viscosity in junior classes, we introduce it as tau equal to mu du dy, or tau is equal to mu into the rate of deformation. There is nothing wrong with it, because it represents the correct form of Newton's law of viscosity for a restricted type of physical problem. For example, when there is only one component of velocity and that also varies along one particular direction. So, that restriction you must tell your students that yes, to represent a simple problem, we are talking about a unidirectional flow along x, and that flow has a gradient along y, and that is the situation when tau is mu du dy. Otherwise, students will have an imagination that Newton's law of viscosity is tau equal to mu du dy, and that is clearly incomplete. If not incorrect, that is clearly incomplete. So, this is something like when we teach our children, say Ramayana, Mahabharata and all these things, it is tau equal to mu du dy is like Ramayana for children, Mahabharata for children, it is Newton's law of viscosity for children. But when it comes to a more advanced stage of fluid mechanics, this is the form of Newton's law of viscosity that you must make your students familiar, and discard the notion that tau equal to mu du dy is the only form of Newton's law of viscosity. We stop here with this and we will continue in the next lecture. Thank you.